Good afternoon, everyone, and welcome to the American Floral Endowment's Grow Pro webinar series. I'm your moderator, Dylan Sedmak. I'm a member of AFE's Young Professionals Council and a regional account manager with Pan American Seed. I received my bachelor's in horticulture from The Ohio State University, and before my time at Pan Am, worked as both a grower and a researcher in the industry. Today's session is on greenhouse climate strategies. On behalf of the endowment, I'm excited to be part of AFE's Grow Pro webinar series that features a new topic every month presented by an industry expert. The webinars are free to everyone thanks to the generous support of AFE sponsors. The views and opinions expressed in these webinars are those of the speakers and do not necessarily reflect the views or positions of AFE. As an independent nonprofit, AFE cannot endorse any specific product or opinion. If you're interested in becoming a sponsor for one of our Grow Pro webinars, you can find that information on AFE's website at endowment.org/GrowPro. Today's session was pre-recorded in English by Dr. Bruce Bugbee. After the presentation, Dr. Bugbee will join us for a Q&A. Feel free to submit your questions to the Q&A feature or chat at any time. We'll answer as many as we can before the end of the hour. Unanswered questions may be answered through a separate email exchange. This session is being recorded and will be shared to AFE's YouTube account. Through YouTube's accessibility features, you can access closed captions in other languages. To get us started, I'd like to share a bit about today's expert speaker. Dr. Bugbee received an MS from UC Davis, his PhD from Penn State, and is now a professor and researcher at Utah State University. He is a past chairman of the Crop Physiology Division of ASA and has authored over 90 referred journal articles. He is also the founder of Apogee Instruments, a world-class manufacturer of environmental sensors. Dr. Bugbee, welcome, and thank you for presenting today on greenhouse climate strategies.
I'm Bruce Bugbee. I'm here in our recording studio today at Utah State University to record this presentation for the American Floral Endowment. And I want to thank the Floral Endowment for the opportunity to do this. I've never got any funding from the Floral Endowment, but that's because I've never asked for it either. But I'm grateful for all the funding that the AFW has made for my colleagues in this. So I'm going to talk a bit about climate strategies and optimization primarily in greenhouses, but in high input agriculture today. And I put a subtitle on here, Can We Achieve Economic and Environmental Sustainability? And I put this up here because sometimes people say, well, if I'm profitable and I'm still in business, then I must be environmentally sustainable. And that especially applies to the electric light agriculture. Staying in business is not the same as being environmentally sustainable. But I'm going to work through some of that in this presentation. First of all, you'll see I got a picture of lettuce, and I'm very conscious that this is not the American Lettuce Endowment, it's the Floral Endowment. But they're both high value, high input crops, related in lots of ways. We mostly work with vegetables here, but everything we do with vegetables is directly applicable to floral. But I want to make a key distinction in how they're different. And this concept, I talk about digital and analog crops. And what's that? Nobody's ever heard of that. Floriculture crops, I'm going to define as digital, and yield crops, like lettuce and tomatoes, are analog crops. Here's the difference. Now with this screen, and let me get this in a nice different color. Let's do this in yellow. So we got input here and output over here. Now output is yield, but all graphs, I'm forever drawing XY plots. This is all of the cost of production. I mean, I guess you could you could even do this in dollars, and this could be dollars, but inputs and outputs. For a floriculture crop, you can have inputs, but they don't result in a saleable plant. And all of a sudden you get to some point right here, and the plant is saleable. And if it's a digital thing, it becomes, this is saleable, this is not saleable. If your inputs go up and up and up, it's not a good return on investment because the plant was saleable right here, and it's still saleable for the same amount of money over here. So the optimum point for floriculture crops would be some here right in the middle where this jumps up. Analog crops are different, and I can show you that in a different color. Analog crops look something like that. You keep giving inputs, you get some yield, but you get to this point here and you keep giving inputs and it keeps going up. So that's why I distinguish digital and analog crops. Other than that, all these concepts are the same. So, one of the things that has transformed greenhouse production and all of agriculture is the advent of very efficient lighting, and especially LEDs. This is a paper we published in the journal Nature a few years ago, and this was part of the history of this agriculture, starting with a kerosene lamp, which is until 150 years ago, that was what we had for lighting. 0.4 lumens per watt. This is the fuel in kerosene and the light output. Edison comes along, boom, a 48x increase to an incandescent bulb. This was incredible. This has transformed the world to be able to use electricity and light. We get up to World War II and we got fluorescent lights, and that was another 5x bump, and everybody, wow, we got fluorescent lights. What a great deal. Then in about the early 1970s, we got high-intensity discharge lighting, a smaller increase, but still a big breakthrough. We switched lighting in factories because of this. And then, of course, finally now, in the last 15, 20 years, another twofold increase in efficiency over this to LEDs. We're at the end of the line because these are becoming 90% efficient. If we go beyond this, it'll be something completely different. Fiber optics or something completely different. But LEDs are fabulous, and I'm not going to talk about LEDs per se, but they've transformed this for supplemental lighting in all cases, whether it's indoors under electric lights or in greenhouses. This is lumens per watt. If we convert this to our efficacy units that many of you are familiar with, micromoles of photons per joule of energy. Look, we start with 0.005, boom, we go all the way up to 4. Now, 4 is a little futuristic. We're not quite there yet with commercial lighting, but I think we can get there in the next 5 or 10 years. But we certainly are at 3 right now. Now let me discuss the implications of this number getting to 3 micromoles per joule. I like to calculate what I call the light to heat ratio. Light is good, heat is generally bad. We're trying to have a lot of light and less heat. We can look at this ratio for sunlight, and it's about 2 micromoles of photons per joule of energy. Now I know that sounds a little odd unit. We can talk about that. 2 for sunlight. Wait a minute, you can go to the store and buy an LED that's 3 micromoles per joule. Those are commercially available. Wow, look at this. You could argue, it's easy to say, we have caught up and passed sunlight for the light to heat ratio. Now think about that. In a greenhouse in the summer, we had too much heat. We're venting and venting all the time. LEDs would be a better ratio for this. So have we made sunlight obsolete? Absolutely not. This joule, we had to pay 10 cents a kilowatt hour to buy it. It is not free. This joule is free from the sunlight, other than venting to get rid of the heat. But here you got to pay for the electricity and you got to pay to vent the heat. So even though this is a striking graph, don't interpret it to say sunlight is obsolete. We're going to just have electric lights, because sunlight we get it all day, every day, for free. Now, here's where it comes from. This is the solar energy distribution. Visible is the same as light. This is the range of photon flux right here. Many of you are really familiar with this. This part out here, we can put that in red, is heat. And if it's the winter, heat's a good thing, but most of the time there's too much heat in the middle of the day. So we want a lot of green and not so much red. If many of you know, we've done a lot of work in this laboratory on far red photons and far red light. If we apply that to this concept, we get another little band in here that's far red photons, 700 to 750 nanometers. And when we know this ratio with far red, that number goes up to 2.3. Gets slightly better for sunlight. Those far red photons came for free. That's where this comes from, this light to heat ratio. But it's very interesting, because I would like to get to the point where we have such a favorable ratio of light to heat that we could air condition greenhouses. And here's the potential of that. First of all, let's do a comparison of greenhouses versus what I call electric light agriculture. If we do photon flux from the sun per day, we get, this is a DLI, 60 moles per meter squared per day. Outside, bright sunny days in the summer, and on those same days, the energy is 30. Let's get to a slightly different color. Same, just different units. This is all heat and energy, total energy, and this is the photon flux. Take a greenhouse. We use greenhouses directly. Transparent structure, no electricity. If a design goal is 70% transmission, that 60 gives us 42 moles a day in the greenhouse. Now, I know this is a high number, but this is all futuristic, what we can get to, and this is a design goal for greenhouses. Now we take this energy and we put it into solar panels. Our commercial solar panels can get up to 20% efficient. 30 times 0.2, we get 6 megajoules per meter squared per day of energy as electricity to work with. Now we feed that electricity to LEDs, and I've put this at 3.5. This is a high estimate, but we're getting there. 6 times 3.5, we get 21 moles a day in electric light agriculture from sunlight, whereas if we build a greenhouse, we get 42 moles a day with no electricity. This doesn't count any of the cost of all this, it's just the conversion. This number, you don't have to have an advanced degree in math to see that this number is twice as big as that number. So what does that mean? You say, well, we'll just put up solar panels and we'll have the electricity. What does that mean? It takes 2 acres of solar panel to light 1 acre of electric light agriculture. That's not a favorable ratio. These solar panels might go in the desert, there might be other places. There's a lot of complications of this, but I think you can see my point. There's inefficiencies of making electricity and inefficiencies of LEDs. As good as they are, the gold standard is still a greenhouse with direct use of sunlight. It gets better than this. Innovations in glass are happening. They have low E glass that helps at night for long wave. This is not low E. This is what we call near infrared reflecting glass. So remember our graph before, here's the light right here, visible. And this out here is infrared. So a typical glass lets everything through. That's virtually all of our greenhouses are clear. It all comes through. The heat comes through in the light. Now with coatings, we can reduce, we can let the visible through, almost all of it, and block the heat. When I did this, when I saw this glass, I'm just stunned because now we get the light without the heat in a greenhouse. A few years ago, my wife and I added on to our house, and I got a glass conservatory out of the deal, and I worked with the architects to put in this low solar gain glass in my greenhouse. I'd like to show you what that looks like. Here's a picture of it. That's a big, it's not very big, but you get the idea. If you look closely at this, we're the biggest citrus producer in Utah, and it turns out that's a coffee tree. And if you do a blow up, we're the biggest coffee producer in Utah too. There's coffee beans in the greenhouse. This greenhouse has near infrared reflecting glass, and I am stunned at how easy it is to cool the greenhouse. Even in the hot days of summer, I get the light without the heat. This is a tremendous potential in the future of greenhouses to better run them year-round, to get the light without the heat. That little thing right there is a module for accurate measurement of carbon dioxide, light, and temperature. One of the great joys of my professional career was 25 years ago starting an instrument company that sells scientific instruments for things. And this is a module made by my company that it's for greenhouse climate control. And it allows me to say all this instrumentation, all the software is continuously getting better. We have more precise control over the temperature for less cost, less energy cost. This and many other things have helped with this. Here's a graph. I think we've all seen this. This is a year, January to December. And here's 15 moles a day. That's about what we'd love to have all the time, 15 moles a day. We get too much in the summer, too little in the winter. We fill this in with supplemental lights and LEDs, and then we still have too much here. But during that time of year, we can go to solar panels above the roofs, tilt them. We can do variable transmission glass, lots of innovations in glazing to help utilize that extra energy that was more than we needed for many crops. And of course, this whole thing is called agrivoltaics. Here's solar panels in the field over crops. This is an emerging discipline. I think it has a lot of potential, particularly in greenhouse. My colleague Eric Runkle at Michigan State's worked a lot with these selective filtering films. In fact, I got these slides from Eric. So there's another innovation in greenhouses that I think is underappreciated for what we can do. Now, I'm going to switch a little bit here to photobiology. We have done a lot of work with colors of light and effects on plant growth. This is a slide from a manuscript, it's 15 years ago, by Broderson and Vogelman, and it's a side view of a leaf. Here's the leaf. I'm going to show that leaf in green right here, the top of the leaf and the bottom of the leaf right here. Blue and red are rapidly absorbed by chlorophyll. They do not penetrate, green penetrates. This is one of the reasons green light is really underappreciated, because some's reflected, but it penetrates deep. Sunlight has lots of green, of course, and we can get green light now from white LEDs, but here's the part that's significant. Boom, far red, 700 to 750 nanometers. Our studies indicate these are photosynthetic photons, and they have a huge effect. They penetrate leaves really well. They have potential for photosynthesis. They can cause all kinds of morphological problems. They're almost always bad in floriculture because they make plant stem elongation, shade avoidance response, make stems too tall. This work on this was done by Shuyang Zhen was a postdoc here. She came to my lab from Mark Van Eersel's lab and worked on this far red light. She is now an assistant professor at Texas A&M. Got a great career in front of her. And this allows me to give a tribute to Mark Van Eersel, who died just a year and 4 months ago from cancer. What a tragedy. Mark was a wonderful colleague. He was a brilliant scientist. We're having a session for him at the horticulture meetings in a couple weeks in Hawaii. I'm giving one of the eulogies to him. What a tremendous scientist. And I know he worked with lots of you on a lot of wonderful projects. He was Shu Young's PhD advisor at UGA. Oh, let's see. I've got the wrong key. There we go. Here's a couple papers. Plant Cell and Environment, Frontiers. These are papers on value of far red photons if you get into the technical parts of this. Far red, it is almost like a magic wavelength for lettuce. In just the right conditions, adding a little far red almost doubles the growth of lettuce. Doesn't happen in all cultivars, in all environments, but it has a tremendous potential to do this. Part of this is leaf expansion. The plant just gets bigger, cell expansion and cell division, but part of it's a direct effect on photosynthesis. For that reason, we have modified the old definition of photosynthetic photon flux density. Used to be 400 to 700. Now we have extended photosynthetic photon flux density, and it goes to 750. So you can buy sensors to do ePPFD. Many of us are making our controls. We're including far red photons as photosynthetic. I'm not going to get into all the details of that, but it's fundamentally changed. Here's a key point. Much of our literature on photobiology was done at very low light levels, like 100 micromoles, just because that's what we could get with LEDs. As we have gotten more efficient LEDs and we have increased the photon flux, we're finding interactions with photobiological effects. Here's a study by Paul Kasuma a few years ago, last year. It's in Frontiers in Plant Science. We added far red, increasing far red to lights, and at low levels, it actually decreased growth. At intermediate levels, there was no effect, and it only had that big beneficial effect I showed a minute ago if the light intensity was high enough. So one of the ways we graph stuff like this is we call it normalization, percent of control. We set all of these equal, and that's what this graph is. And now these effects get real apparent. In this study, with this lettuce, at low levels, far red was detrimental, and at high levels is highly beneficial. I think this is worth all of us looking at interactions between effects that we see in low light, and we got to be very careful to extrapolate from low light to high light. I think there can be significant interactions in here. A few closing slides on recent work I think is going to be real useful to a lot of people. These are just our tests of instruments and things. This is what we call a pointed tip electrode. I don't own stock in this company, but you can buy these online. This is made by Hanna Instruments. There's a big picture of it. We've done a lot of testing with these now. We own several of these in the lab. Here's the paper, Langenfeld, Skabeland, and Bugbee. It's in Frontiers in Plant Science last year. This is a tremendous electrode. I think our paper shows it's even more accurate than the old leachate method to do pH, because it starts to get at rhizosphere pH. Look at the paper. These are not, they're a little bit more than a pH electrode, but we've really found these to be remarkably stable and remarkably useful. silica in media, underappreciated the values of it. This is another paper, Mackenzie Day, Jennifer Bolt, who was probably listening, and myself last year, dissolution of silicon from media. Here's the take-home message. Wollastonite is a tremendous additive. It works well. So do rice hulls, either one. They depends on what's most cost-effective to put in. You can replace part of your lime with this. There is no reason not to put these in media. Silica it might help a little, it might help a lot, but it never hurts. You can't get too much silica in there. Take a look at the paper. This is just release rates over a long period of time, and the lines all slope up. So either one of these works well. Read the paper. We've done a bunch of studies on dwarf tomatoes, lots of new genetics coming out. This is a paper where in this paper right here, it's on Digital Commons. We reported in our studies Regina Red at our light levels was the most promising cultivar. And then we went to order more seed, and the company said, oh my God, you published that paper, now we're all sold out of seed. So we had to grow our own seed of this. But this is a test of multiple dwarf tomatoes. Several other people have done studies like this. Selena Gomez at Purdue. We're now doing another study with even newer genetics. There's a lot of interesting genetic options for dwarf tomatoes now. The flavor's getting better, the yield is getting better, and they're more dwarf. Finally, I'm going to close on nutrition. I'm teaching a class right now on plant nutrition. We are working toward, with help from NASA, we're working toward nutrition with zero discharge, never any leaching. It's all fertigation at exactly the right dilution, so the nutrients are never deficient and they never accumulate. This started 20 years ago. I published a paper on nutrient management, and that has over 400 citations. It's one of my top 10 cited papers of my career, but it's old. So 2 years ago, my student Noah Langenfeld, and there he is, Noah Langenfeld, collaborated with some people you know, Jim Faust, Royal Hines, Daniel Fernandez, to write a paper on update, principles of nutrient management, and this is 40 citations and counting. I'm real pleased people have assigned this as assigned reading to classes and principles. Here's how it works. We can grow crop after crop after crop in the same media, no leaching. This is Mizuna lettuce. We put on dilute fertilizer in, and then we harvest and replant in the same media. The roots regrow. We call this no-till agriculture, which is a fundamental principle. But if we can get this going for indoor agriculture, greenhouses and indoors, what a tremendous thing. We're not shipping media outside all the time. We're replanting in the same media. This is done in peat. I'm going to stop right here and take questions. This is exciting work. This gets me out of bed in the morning to come and work with my graduate students. And once again, I'm very grateful to this opportunity to talk to the American Floral Endowment. And I'll close here and take any questions. Thank you.
Thank you, Dr. Bugbee. Dr. Bugbee will be joining us here soon. There were some technical difficulties getting him on. But in the meantime, I did want to say thank you again for attending today's webinar. Hopefully you learned something. And just a reminder that next month we will be having another webinar with Dr. Dayton Wild, who will be presenting Success with Tissue Culture, which is on Tuesday, October 2nd at 1 p.m. Eastern. And again, you can register for that at endowment.org/GrowPro. And then just make sure that while you're there on the website to check out our past webinar recordings and lots of other grower-related resources, research reports that are all available for free, thanks to industry support. I know I've used a lot of the resources myself. They've been very helpful. And then also just a reminder too, as we're waiting, that there will be a brief survey about today's session afterwards where you can suggest additional topics and really help us to continue to improve these webinars. So I'd say in the meantime, if you wouldn't mind, if you have any questions, feel free to start submitting them in the chat. Thank you. Okay. Looks like he's here now. So I will actually go ahead and start reading some of the questions. So I have one here. It says, in no-till agriculture sounds so interesting, but is it more vulnerable for diseases?
Hold on, let's get we just got our recording studio room joined by computer, so I didn't have to do this from my office. This is a little bit nicer. Yeah, could you repeat the question, please?
Yes, Dr. Bugbee. The question was, in no-till agriculture, it sounds interesting, but is it more vulnerable for diseases?
Is it more what?
Vulnerable for diseases.
We just, this morning, we had NASA is here visiting the lab. We get a lot of funding from NASA. And this exact question came up because we're building a new plant growth chamber for the space station. And that's this no-till agriculture. We're replant in the same peat over and over again. And the best answer I can give to that is the safest approach is a robust microbial community in the root zone. NASA's used to sterilizing everything. I mean, it's the opposite of drinking bleach. I mean, you just have a really robust community. And now the pathogens can't get started because they have to compete with all the beneficial microbes in the root zone. So we've got a few decades of experience in terrestrial agriculture with no-till agriculture, and the answer is we do not see an increase in disease. So it seems odd, but we're anxious to bring high input agriculture in greenhouses up to the same no-till level that we've been doing in the field, so we don't have to discard media. And fortunately, because with NASA's help, we can do some cutting edge studies with this, with replanting in the same media. But it's that robust microbial community. Once that's stable, we do not see an increase in disease. Doesn't mean the diseases go away. It doesn't make it worse.
All right, thank you, Dr. Bugbee. Several more here. Does far red light also reduce the risk of tip burn in lettuce?
Good question. Not necessarily. Far red light fundamentally increases cell division and cell expansion, so you get bigger cells, and by virtue of growing faster, it could increase the incidence of tip burn. And now I'm thinking of all the literature. We have done lots of studies on far red, and we haven't seen an increase. But I'm trying to think if any of my colleagues have specifically looked at far red and tip burn, and there might possibly be some literature on this. If it does increase tip burn, it's not a dramatic increase. But it might be a small increase. But here's the underlying thinking. Anything that makes lettuce grow faster makes these leaves expand faster, and that in turn increases tip burn, which is the tiny meristematic leaves down they can't get enough calcium. So it is possible that far red could somewhat increase tip burn incidence. We haven't specifically studied that in this lab, but this is a whole different topic. But I can tell you one of the biggest ways to get rid of tip burn is, first of all, genetics. Just choose lines that have minimal tip burn. That's huge. Then after that, surprisingly, we want to have dilute nutrient solutions. Those actually help transport water to those young leaves, and those dilute nutrient solutions reduce the incidence of tip burn. that's a whole nother topic, but maybe in a few years I'll do another floral endowment seminar on that topic.
Thank you. Another here on light. How can light spectrum be used to control or reduce foliar diseases?
Again, going back to first principles, if cell division and cell expansion is increased, you got to think it assumes these are bigger cells with thinner cell walls. And so thinner cell walls are more like plants in shade. We're tricking the plants to thinking they are in shade. So there's potential increase in disease, in pathogens. But once again, good hygiene is critical. Good air movement is real critical to that. So it's certainly high levels of blue light, for example, do the opposite of red. They make the plants more compact. So more compact plants could potentially lead to less disease, but then you don't have as much plant to sell either. So there's trade-offs with this. But I would fall back on best practices in any growth facility. Good cleanliness and good airflow are huge factors. And spectral quality could be in there, but I think it's a lesser factor than those other best practices.
All right, thank you. I got several more here. Lots of questions in the chat. Are there some good sources of micro-dwarf tomato cultivars we might use for trials?
Yeah, we've done tons of studies. In fact, if we had a mobile camera, we'd walk right out to the greenhouse now. I could show you our dwarf trials. I know that Johnny's Selected Seeds has a bunch of dwarf cultivars. Selena Gomez, and I mentioned this at Purdue, has a paper on dwarf cultivars. We have a paper that's online. If you search for Langenfeld and Bugbee, you'll find it in USU Digital Commons. We are continuing to trial these dwarfs, and we keep discovering breeders that have come out with even more dwarf cultivars. Now, they don't taste as good as big cultivars, but they're compact. I mean, we get lines that are 15 centimeters tall, and a lot of small fruit. But I would look for the seed companies and do online searches for dwarf tomatoes. I mean, I think you'll find a wide range of dwarf tomatoes. The classics are Micro Tom and Micro Tina. Those were done, 20, 30 years ago by a breeder in Florida. His last name was Scott. And those are real tiny, maybe 10 centimeters tall. But now breeders have tried to get more flavor and without having too much of an increase of plant height. But it's an exciting time for tomato genetics. And I would encourage everybody to get seed and try them. There's a big interaction with light level. If you grow them in low light, they're going to be taller. And if you can get higher light, it'll help keep the plants more compact and lead to much better flavor of the tomatoes.
Yes, thank you, Dr. Bugbee. I'll also just mention too, so since I work for Pan American Seed, we do have some of those dwarf varieties in our kitchen mini assortment, as well as some of the other breeders out there as well. So feel free to take a look at those. The next question is, have you had success in using fumigating mustard have you had success in using fumigating mustard in no-till practices if disease is present?
In using fumigating.
Sorry, I think the question, let me reread this. Have you had success in fumigating mustard in no-till practices if disease is present?
Yeah, in fumigating the media. Is that
Yes. I think presumably, yes.
Yes. We haven't done it, mostly because we haven't needed to. Now, for sure, if you got some pythium in there, moisture got a little too high, you could get pythium in there. Mostly what I would do for that is try and get the water down to try and reduce pythium. But the quickest answer is no, we haven't worked on fumigating here, but that would be a good technique as we do that in commercial agriculture all the time, methyl bromide for strawberries that gets rid of nematodes. That would be a good technique. We just don't have experience with it in this lab.
All right. And the next one is, are there any studies or papers on managing weeds based on DLI?
Any studies on what using DLI?
Studies or papers on managing weeds based on DLI.
Managing the leaves?
Weeds.
Oh, managing weeds?
Yes.
Not that I know of. Usually weeds aren't a big problem. Weeds are a big problem in terrestrial no-till agriculture, to be sure, but they've not been a big problem in our soilless media. And I'm not, even if they were, I'm not sure that DLI would help us. I mean, I think you want to have DLI as good as you can because that generally favors the crops. They're adapted to very high light. So we don't have an experience with that here.
Okay, just a few more here. What is the biggest benefit of adding silica in the media compared to lime?
There's a long list of claims for beneficial effects of silica. And if we sort of go back to first principles, that's what glass is silicon dioxide. So this silica ends up in the cell walls of the plants. And we like to say it makes the plant structurally stronger. And there's quite a bit of evidence for that in high silica accumulators, rice and wheat. Just the leaves are more erect, they're just structurally more rigid. And then we move to soilless media and soilless media components, and there's virtually no silica in them. So suddenly we get a situation where we get artifacts because we don't have this common element that's in all field soils. We just don't have it. That structural rigidity, I would say the biggest single advantage we see here is a significant reduction in powdery mildew. We've had cases here where no powdery mildew, and then we get an outbreak. And what's going on? And then we found out something happened to our silica injector system and it stopped. And we get it fixed and the powdery mildew goes away. So it depends on crops, but that's a known significant advantage of silica. It also has a protective effect against micronutrient toxicities. Without silica, manganese and zinc toxicities can be much worse. Plants are more susceptible to those. So it has a stabilizing effect on nutrient uptake. And there's claims that it helps make plants more tolerant of water stress. That's we've tried that and it's a little difficult to demonstrate. But in theory, it makes the roots stronger too, not just the stems. And in drought stress, you don't want your roots to die. You want them to tolerate the drought stress till you get to rewater. And so our thinking is that it helps plants tolerate drought better as well. There's not always rigorous academic proof of these things, but like tolerance of water stress. But my own personal and thinking is that probably helps with water stress. We just haven't been able to clearly demonstrate it yet.
Great. And then along the same lines, could it be applied through a liquid fertilizer regimen?
So it's coming through say the question again.
Sorry, is it possible to add the silica through a liquid fertilizer program?
Good question. Yes, as you can see from my talk, we add it either as wollastonite or risols in media. So that's clear. You can read our paper on that and get the rates that we added at. Like all nutrients, the best way is liquid fertilization because it gets a steady supply. And yes, it's possible. And yes, we do it here. Brendan Fatzinger and I have a paper on this online. It's through Utah State University Digital Commons. Silica is one of those rare elements that gets more soluble at high pH. So you have to have a separate injector and a separate tank, and you have to keep that tank at pH 11.2 or higher to keep the silica in solution. And once you do that, we put silica in solution in all of our injectors around here. So it's added every day, but we have to maintain those tanks at a high pH so it's in solution. If the pH drops even to 10, we start to get a white cloudiness, and that's tiny precipitates of silica, and they wear out the piston in the injectors. So you have to be certain that the stock solution stays clear, and it stays clear when the pH is very high.
All right, thank you. And then regarding light, again, what would the impact be of using glass restricting far red light on flowering in greenhouses?
Yeah, far red light in flowering. Now, our colleagues at Wageningen, Leo Marcellus, and my former PhD student Paul Kasuma is over there now. I've done a lot of work in tomatoes, using far red to accelerate flowering and improving harvest index in tomatoes. And I would say there's a small but statistically significant effect of in tomatoes of the increased rate of flowering from far red. We haven't done those studies here. We've mostly worked with far red in leafy greens. But there's the potential to alter carbon partitioning to fruits with far red as well. Again, we got to be very careful because it's almost like a blowtorch. You get too much and you get tall plants. So you got to time the delivery and time the amount to get the beneficial effects without the detrimental effects on increased internode elongation.
All right, thank you. And then regarding climate control technology, have you assessed different climate control technologies? And then secondarily to that, if so, could you comment maybe on how frequently a greenhouse should update its software technology?
Um, I think this is generally about cutting edge of control systems for greenhouses. And if I could summarize the points I was making early in the seminar, it's so much of this is the heat to light ratio. Light is good, generally heat's bad, you got to vent, and if we can fundamentally alter that ratio of heat to light, we have to realize the amazing benefits of high carbon dioxide levels in a greenhouse. And we got great modules now, fast response. And another huge breakthrough in this, I didn't mention it, is variable frequency drive fans, VFD fans. We've now upgraded all of our fans here at Utah State University to these modulating fans, which they last much longer and give us much more steady state control than the old fans, which are on off. And I'm sure lots of growers listening already have done that and they know about it. Those fans have gotten way better and way cheaper. That's a huge, to me, that's one of the big breakthroughs in cooling technologies for greenhouse. But yes, there are computer systems better all the time. They allow more sophisticated algorithms. I'm personally interested in control systems based on 1 second to the next measurement of light, the thermal, a light sensor, a photon flux sensor, or an energy sensor. And if the sun goes behind a cloud, you know you're going to need heat within the next few minutes. You can start doing that before you need it. And the reverse, if the sun comes out from behind a cloud, you can be ready to start cooling when you need it. This is anticipating heating and cooling requirements based on the solar radiation coming into a greenhouse. And those changes happen over seconds on a cloudy day. So I think that's another example of cutting edge technologies for climate control that we're going to start utilizing. Better plant growth and reduced energy costs for temperature control.
Okay, thank you. And then just one more here on silica. How does silica interact with the fertilizer in the irrigation system after being injected? And can it be added to water held in an overnight storage tank?
Yes. Silicon can precipitate other elements, but if you keep it dilute, and dilute is 0.3 to 0.6 millimolar, which are 10 to 20 parts per million elemental SI, then there's not a problem. The problems happen if it's in a concentrated system. You can mix a solution of silicon, and in fact, our stock tanks are like that. They're concentrated 100 times with the high pH, and they're stable for weeks and weeks and weeks, months, as long as we keep the pH high. I should mention, by the way, that a high pH solution absorbs carbon dioxide from the air, and that makes it gradually go more acidic. So in our stock concentrate tanks, we float a disc of polyurethane foam on the surface to minimize that exchange of CO2 with the atmosphere. It keeps the tank stable over months in the stock solution. But even overnight, you could mix a solution overnight, a dilute solution, and you'd certainly be fine as long as you got it in solution. So the solution was clear to start with.
All right. And then just along those lines, for silica, any recommendations when sourcing wollastonite as a silica soil amendment?
We get our wollastonite through Vansil Minerals, which is a VANSIL. I think their headquarters in New York State. And we buy the coarsest grade they have. That's still plenty fine. Silica is used in lots of different things, food thickeners and food products. We want a slow release. So it's in our paper that the coarseness grade, but it's the most coarse grade. And it looks like dolomitic lime. It looks like any kind of lime. It's a white powder, and we mix it in the exact same way. Some people have been concerned about the dust coming off it, but at the levels we use it, and as soon as it gets it all moist, you don't have dust. Inhalation risk, but you could worry the same inhalation risk would be true of using lime products too. Dolomitic lime, hydrated lime, those are all similar white powders. In fact, they're so similar, you got to make sure you keep track of what it is, because somebody might get them mixed up. I know some growers have looked at substituting wollastonite for lime in their mixing systems. It's a much slower release pH control than even calcitic or dolomitic lime. So usually you have to use some of each, but if you use more wollastonite, you can substitute for the lime and get pH control.
Thank you. And then a few on light. One guest would like to know if it's better to measure PAR inside the greenhouse or outside with a PAR sensor.
Yep, all good questions. Ideally, the simplest thing is greenhouse is shade, right? So, and that means you should measure it inside the greenhouse. But that means you got to have a lot of different sensors in different places in the greenhouse. And if I was going to tout some claim for an instrument company, I would say buy a lot of sensors and measure it everywhere. That's not how we do it here in our research greenhouse complex. We make one measurement outside the greenhouse, and then we calculate the transmission of light for different greenhouses. Some of them are 50%, so we multiply by 0.5. Some of them are 60, so we multiply by 0.6. And some positions might be 0.65, some might be 0.45, but we've characterized the greenhouses so we can make one measurement outside and then predict the light level at many, many places inside. Because once you get that number for percent transmission, unless your glass gets dirty, that number is a constant. It's close to a constant year round. And that way you can get away with one measurement above the greenhouse and then calculate what it is inside. A rule of thumb is 0.5. If you just measured it outside, that's a rule of thumb we often use. But that number can vary plus or minus 25%, depending on the greenhouse.
Yes, and speaking of glazing, would you be able to explain some of the seasonal differences in temperature if you use near-infrared reflective glass? And will the greenhouse get too cold in the winter because of it?
Yes, so if you use this near-infrared reflecting glass, which, as I mentioned in the seminar, I built my home greenhouse with this stuff. And it's more money, but the price is coming down. So I have to use more heat in the winter. My greenhouse doesn't heat up as much in the winter as it would with regular glass. So my heating costs go up in the winter, but my cooling costs go way down in the summer. And if you do evaporative cooling, that's so cheap that maybe you just use regular glass and do evaporative cooling. But I like to keep the air condition and keep the CO2 inside. That's a huge advantage for crops. And I think it's an underappreciated advantage. But the bottom line is, yes, this near infrared reflecting glass means you have to use more energy to heat the greenhouse on the cold days of winter.
All right, thank you. And then also regarding this, would you be able to explain the difference between low E glass and some of the new near infrared reflective glass?
Yeah, good question. This now, I'm going to try and explain radiation physics in 30 seconds. We lose heat at night by infrared emissions through the glass. It's cold outside, it's warm inside, there's radiation that goes right through the glass, and that's a lot of heat loss. Low E means low emissivity, and it's really like an aluminum foil coating in the glass that reflects the heat back in. And that's been around now for 20, 30 years. And I think all glass is low emissivity. And that helps primarily at night keep the greenhouse warmer. A different coating, also visually transparent, is this near infrared reflective coating. And that's almost like a silvery surface that reflects thermal radiation from the sun back into the atmosphere. So that works in the day to reduce the thermal gain. There are two coatings, both transparent, but one's shortwave thermal radiation from the sun getting reflected, and one's long wave radiation from a warm exterior to the cold night sky. They work in different ways, and they supplement each other.
All right, thank you, Dr. Bugbee. And I think that about wraps up all of our questions. So thank you very much to Dr. Bugbee for his class and for answering all the questions. And thank you to the audience again for attending. Just a reminder, like I said earlier, next month we will have another speaker, Dr. Dayton Wild, presenting success with tissue culture, and that's on Tuesday the 22nd at 1 p.m. Eastern, which you can find on the endowment.org/GrowPro website. Just make sure too that you complete the brief survey about today's session, where you can suggest additional topics and help us continue to improve these webinars. So thank you again, everyone, for joining us, and hope you all have an excellent day.
Thanks.